example for using the constant velocity or constant acceleration, let's say the uniform translation equations. These are good equations to memorize, but remember that it can only be used in these special cases when either we have uniform translational motion, constant velocity, or we have uniform acceleration right there, or constant acceleration. So here's a problem. I think this is from the 8th edition of Beer Johnston. It might also be the same as what's a current one, but I know that when this was picked out, it was from the 8th edition. All right. So this could actually be like a projectile motion problem, just by the way, but it's only in one dimension, so that still kind of works for our purposes. So we have a group of students. They launched this model rocket up into the air. Based on the tracking data, so somebody's collected data, they determined that the altitude of the rocket was 27.5 meters at the end of the powered portion. All right, that means that it's not a kinetics problem, right? After that motion, there's no forces going on right at that 27.5 meters. So we can use kinematics from there on out. And the rocket lands 16 seconds later, right? So this is data that they've collected. Maybe they used a camera or something, and were able to estimate how high it went up, or how high the rocket stopped. So it keeps going up. It's going to reach a peak and then start coming down. And between that and that was 16 seconds. Knowing that the descent parachute failed to deploy, so the rocket fell freely to the ground after reaching its maximum altitude, and we're going to assume that the gravity is 9.81 meters per second squared. We want to find the speed of the rocket at the end of the powered flight, right there, right? And then the maximum altitude reached by the rocket. So even though these seem like easy equations to use, this has already turned a problem kind of on its head, and so you're going to have to be careful not to underthink it, right? Or not to overthink it. You want to make sure that we're picking the problem apart. All right, so we say, this is a lot of information. How do I go about trying to figure this out? Well, I drew a little sketch. I think little sketches can really help, right? So let's say here's the ground, right? There's just not enough room up here, up above. That's what I'm going to do. And I'm going to say here's my little rocket right here, and this is my 27.5 meters right to there. Let's call this time 1, or position 1. It's going to come up, and I'm going to draw it like it's coming in a loop, although it's supposed to come straight down right there. And I'm going to say this is T2, or time 2, or position 2, whatever you want to say. And then this is position 3 right here. So we're going to do that. We do this in stages, and we know that the acceleration is constant, negative 9.81 meters per second squared. We're going to treat this thing as if it's going in a dimension like that right there is going to be positive, right? So we know this, and this is very similar. We do very similar things when we solve problems. We're going to write down the things that we know, maybe come up with sort of a plan, kind of to help us think our way through all of this. So at t1 equals 0, right? So this is time 1. When that is equal to 0, we know that y, we'll call it y1, is equal to 27.5 meters, right? All right, so what else do we know? We know that here at the end, at t3 is 16 seconds. We know that y3 is equal to 0. All those things seem like it's true. I think so. So what we can do here is we could figure out what the velocity was at then. We could take it between 1 and 3 because the acceleration is always this amount right here. So we could use the fundamental kinematic relation that we want to use is double checking here. This is position and time, right, that we have going on right there. So that this would be a good one to do. And let's take it between 3 and 3 and 1, right? So we say that y3 is equal to y1, right? Plus the initial velocity v1 times t3 plus 1/2 acceleration right there, t3 squared. We've just plugged those in. So now we can put in the things that we know. Well, actually, just going through this, we know the position y3, we know the position y1. We don't know this, but that's what we were trying to find out. We're trying to find the speed when the rocket, and at the end of the rocket flight. This guy right here, we're trying to find its velocity here. Here's what we don't know. Here's where we know that this is the end time. We know this acceleration, they told us, and here we know this end time, right? So we know everything except for that velocity, so we can find it out. So we say 0 is equal to our 27.5 plus v1 times 16 plus 1/2, and I'll put this negative in here. So why is that negative? Because it's going in the opposite direction of what I decided must be my coordinate. Must be y going up right there. And 16 squared right here. So if we do that, we can figure out the velocity at the beginning is 76.76 meters per second. Now they asked for the speed, so we don't need to make this a vector. If we did, we'd put a hat on top of it, and we would put an arrow indicating its direction, right? But they only asked for speed, which is the magnitude of the velocity. So we also want to find the maximum altitude that it reached by the rocket. Well, that's going to be at 2 right there, but we don't know when that happens. So we can't use, well, what are we going to do? Well, if we go back to our kinematic relations, we'll notice that we have a wild card here where we have velocities and positions. Let's see, I guess I'll use this guy right here. And we have acceleration. So, and it doesn't have to be x. It could be any variable. So we could use this as y. So we could write out that v2, let's say, squared is going to be v1 squared, right? Plus a, which is a constant, times y2 minus y1. You see how that works? And so what we can do here is, we can go ahead and find out at 0, right? That's at we know the velocity is going to be 0 here because it's going to pause at the top. It's going to go as high as it can, and it's going to start falling. Squared is going to be equal to our 76.76 squared plus negative 9.81 y2, which is what we're trying to find, minus our 27.5. And what we end up finding is that y2 is equal to 327.8 meters. And that's the answer. Now, what can make dynamics problems hard is we might not ask you part A. And that could be very frustrating. If we just ask for the maximum altitude and we gave you all this information, you might start equation hunting and throw your hands up in the air. This is what we have to try to get over. This is maybe a holdover from some of the previous education that you've been gathering, where we just kind of try to do stuff in one step. And the path to getting to a solution is fairly straightforward, right? Maybe doesn't even require many steps. But quite often in dynamics, And what we'll be asking you to do is you might have to try a couple things. Like it might not be obvious to you and when you start a problem how to get to the end result. So you have to kind of like go down. I like to describe it as going into a maze and trying to find your way through a maze. You might hit some dead ends, but you got to try something, go down one path, and then say, okay, we'll backtrack a little bit if that doesn't work out and try something else. So hopefully the idea, if you were given this problem and you were going to be successful in it, that you might first jump over to this equation and say, no, man, but I don't know what that velocity is. And then a light bulb would go on in your head. Said, yeah, but I could find out what that velocity is because I know the times. So that you would do this first step without being asked for it as part A. That is where a lot of the dynamics problem solving practice that you'll get this semester will have you starting to think and pick problems apart and look for a way to navigate to a solution. So I think that's a great skill set to have for an engineer and to be a problem solver. So here you go. That's the end of the example, and I think I'm going to do dependent motion, relative motion and dependent motion introduction in the next video.